This model is called the logistic equation. Okay, and here we're assuming that x of t is a state variable denoting population size. It could be population size or it could be density, right? But x is a function of t and it denotes some type of volume, density, or population size. And the parameters, so here x is the state variable, and then we have two parameters. We have r and we have this parameter k. Okay, so let me clear this here. K is, in this model, we refer to K as the carrying capacity. The carrying capacity of a population has to do with basically the number of individuals that can be sustained in the population. Okay, so it has to do with the availability of resources for that population to sustain a specific number of individuals. On the other hand, the parameter R has to do with the rate of growth. Specifically, it's called the intrinsic growth rate. And this parameter has the meaning of is quantifying the attained per capita growth rate in the case when the population size is so small that basically resources are very available, right? There is a limitation of resources can be neglected due to the infinitesimal size of the population. Of course, I'm skipping several steps here. This is the ordinary differential equation. And there are methods for computing. This is one of those ODEs that you can find an explicit solution for this differential equation. There's something called separation of variables, and you can find that this expression here is the solution. This is the solution of that ODE. That means that this function, this expression, that is a function of time, but it has parameters k, and it has the parameter r over there. This function satisfies that ordinary differential equation, right? So that's what it means for this to be a solution. So this is a well-known curve. It has, you can argue this has the shape of an S, of the letter S, right? So you just have to have very good imagination as you're stretching that S. This curve has that type of shape. These curves with this shape are very well known in population dynamics and theoretical biology, and certainly in many other applications. One of the important things is easy to see here that if you take the limit as t goes to infinity, you'd be taking the limit of this expression here as t goes to infinity. Then as t goes to infinity, the only part of this expression, this is a ratio, the only part that has t in it is that exponential with exponent is e to the minus rt. So as t goes, we know that e to the minus rt, this goes to 0 as t goes to infinity, which means that this limit becomes k times x0 over x0, and this becomes k. So the limit, basically what we're saying here is that x approaches k. Here, x, from this calculation, we're concluding that x of t approaches the parameter k. X of t approaches the carrying capacity. So that's the x of t, the population size or population density, when governed by this equation, is such that this is telling us the population size will approach the carrying capacity. That's exactly what we're able to verify when we have a numerical solution of this equation. The fact here, this is t and this is x of t, and this curve is behaving in this form. So that means that the fact that x of t is flat, right, is telling us that x of t is converging to a horizontal asymptote. Here, this k value is a horizontal asymptote. And so turns out that to come up with this illustration, you have to plug in specific values for the parameters, right? This is a mathematical model. It's an equation. If you have parameter values, then you're going to obtain a numerical solution, right? And so what we can conclude here from this illustration is that this value at which x of t is converging, it seems that here k is approximately 400 based on what the graph is telling us, right? So this logistic curve, this type of growth is well understood. It's called logistic growth, and basically we just summarize several features of this.